Coffee is one of my favorite things in the world. I like a simple cup of black coffee, but sometimes I like to switch it up. Are you someone who likes a plain cup of black coffee? Or are you one of those people that likes the more dressed up versions of coffee? Adding more ingredients like milk, flavored cream, or hot chocolate are ways of changing a cup of coffee. We may still think of it as being a coffee-based beverage, but there are expected differences between black coffee and more fancy versions of coffee like a latte or espresso. Regardless of what type of coffee we're drinking, the effects of each ingredient used don't change. For example, coffee will always act like a stimulant because of its caffeine content. This doesn't change if we add milk, change the brewing style, or if it's served at different temperatures. Coffee will still be a stimulant. This holds true for anything that you add to coffee. Someone who's lactose intolerant would still be unable to consume dairy products, even if they were mixed in with coffee. The lactose in milk doesn't change because it's mixed with something else. Even though every ingredient continues to hold its own characteristics, combining them creates a new beverage that may be more enjoyable than when consumed separately. In software, like devising a new beverage, it's beneficial to have flexible combinations of overall behaviors. But we encounter an issue trying to do this dynamically at runtime. That's because the behavior of an object is defined by its class. But the notion of a class and relationships like inheritance are static, that is, happen at compile time. This means that we cannot make changes to classes while our program is running. We'd need to create a new class in order to achieve a new combination of behaviors. As a result, having lots of new combinations would lead to lots of classes, and we don't want that. Given that an object has a certain behavior, can we still, in effect, dynamically attach additional behaviors or responsibilities to it? Luckily, there is a decorator design pattern to achieve this. It uses aggregation to combine behaviors at runtime. Aggregation is used to represent a has-a, or weak containment relationship between two objects. We can use the has-a relationship to build a stack of objects, where each level of the stack contains an object that knows about its own behavior and augments the one underneath it in the stack. This is what an aggregation stack looks like. Object A is a base object because it doesn't contain another object. It will have its own set of behaviors. Object B aggregates Object A, allowing Object B to, in effect, augment the behaviors of Object A. We can continue to add objects to the stack in such a way that Object C aggregates Object B to, in effect, augment the behaviors of Object B. The aggregation relationship is always one-to-one in the decorator design pattern in order to build up the stack so that one object is on top of another. To achieve an overall combination of behavior for the stacked objects, you would call upon the top element, which is Object C. Object C would call upon Object B, and Object B would call upon Object A. Object A responds with its behavior, then Object B adds its increment of behavior, and then Object C adds its increment of behavior. The actual structure of this design pattern makes use of both interfaces and inheritance, so that the classes conform to a common type, whose instances can be stacked up in a compatible way to build up a coherent combination of behavior overall. Now let's look at how the decorator design pattern is structured with a general UML class diagram. The component interface is used to define the common type for all the classes. A client class will expect the same interface across all the component classes. A concrete component class implements the component interface and can be instantiated. An instance of this class can be used as a base object in the stack. Decorator is an abstract class. Just like the concrete component class, it implements the component interface. The main differences are that decorator aggregates other types of components, which will allow us to stack components on top of each other, and decorator serves as the abstract superclass of concrete decorator classes that will provide an increment of behavior. We build the stack of components starting with an instance of the concrete component class and continuing with instances of subclasses of the decorator abstract class. In terms of our coffee analogy, the concrete component would be a black coffee. Decorators for our coffee would be milk, sugar, hot chocolate, and any other ingredient you could add to a coffee. There are many analogies that can be used for the decorator design pattern, from coffee to pizza, but these analogies don't translate well to how you would actually make use of this design pattern for software. So let's look at an example that is more realistic to what you would see in a software system. A web page is an example of where we would use this design pattern. A basic web page is simply a markup using HTML with style sheets and possibly some JavaScript. However, the behavior of a web page can be more complex. What if you want to make sure that people accessing your page are authorized? Or what if you want to split a large number of search results into separate pages? You don't want to write completely different web page types for every possible combination of web page permission, pagination, or caching behaviors. Instead, you can use the decorator design pattern to create one class for each type of behavior and build the specific combination of web page that you want at runtime. Let's take this example and see what it would look like in a UML class diagram by following the general design for a decorator design pattern. Your component interface is a web page. This will define all subclasses in the pattern as a type of web page, which have their own implementation of how to display themselves. The concrete component class is your basic web page. It consists of HTML, a style sheet, and scripts, which we will represent as strings for the sake of simplicity. This basic web page should know how to display all of its web page elements. Now, you need decorators to add more functionality to your basic web page using aggregation instead of subclassing the basic web page itself. You will need to use subtypes of the abstract web page decorator class to augment our basic web page. As we explored earlier, the web page decorator will be a subtype of web page. Therefore, a subtype of the decorator is also a subtype of the web page interface. You can define any number of additional behaviors you want to augment your basic web page with. In this example, we will enhance the basic web page by adding authorization to ensure the user can access the page, and authentication to make sure the user is who they claim to be. Can you see how this reduces the number of classes we would need to create? If you used inheritance of the basic web page, you would need to create a class for every combination of these behaviors. That means we would need a separate class for the combined authorization and authentication functions. The decorator design pattern addresses this problem by allowing concrete decorators to aggregate any type of component. Now, let's take a look at how we would implement this design. Step 1. Design the component interface. First, you define your interface that the rest of the classes in the design pattern will be subtypes of. The interface will define the common behaviors that your basic web page and decorators will have. Step 2. Implement the interface with your base concrete component class. Your basic web page will implement how it will display itself by using standard HTML markup and page element styling defined in the cascading style sheet. Your basic web page will also run some basic JavaScript. This will be the base building block for all web page objects during runtime. Step 3. Implement the interface with your abstract decorator class. The implementation of the decorator class is important despite how little code there is. The first thing to note is that a web page decorator contains only one instance of web page. This allows us to stack decorators on top of the basic web page and on top of each other. Each type of web page is responsible for its own behavior and will recursively invoke the next web page on the stack to execute its behavior. The constructor will let you link different subtypes of web page together in a stack. All you need to do is tell it what instance of web page subtype you want to stack upon. Since the constructor allows you to link any web page subtype onto the stack, the order in which you build the stack matters. The important part is that the basic web page must be the first one in the stack. The rest of the ordering will depend on the design of your system and which augmenting behaviors you want executed first. Your abstract decorator simply delegates the display behavior to the web page object that it aggregates. This will let you combine the display behavior down the stack of web pages. Step 4. Inherit from the abstract decorator and implement the component interface with concrete decorator classes. The constructors will use the abstract superclasses constructor since it will allow us to stack the decorators together. Remember that the abstract web page decorator class handles the aggregation of the concrete decorator classes. Each decorator has its own responsibilities. You implement these responsibilities within the appropriate classes so that they can be invoked. In order to recursively call the display behavior, the concrete decorators invoke the superclass's display method. Since the abstract decorator superclass facilitates the aggregation of various types of web pages, the call to superdisplay will cause the next web page in the stack to execute its version of display until you get to the basic web page. The recursive call will end here because the basic web page is the concrete component, which does not aggregate any other types of web pages. The idea here is to link the calls of display all the way to the bottom and bubble the execution back up. This makes sense because you need to build your basic web page before you can add more behaviors to it. Now that you've completed your decorator pattern, let's see it in action. You build your basic web page first, add the authorization behavior next, and then complete the web page by adding the authentication behavior last. This way, when the display method is called, it will link the method calls down to the basic web page. The basic web page will display itself, and then the display call will move back up the links to the authorized behavior first and the authentication behavior last. The output of this program would look like this. If we refer back to our aggregation stack diagram, the invocation of display looks like this. As you can see, you can add any decorator to the basic web page to achieve a different combined behavior. This allows you to dynamically build up the behavior of your basic web page because we can instantiate and add new objects to the aggregated stack. The decorator design pattern is capable of letting you embellish your objects in a very unique way. To summarize, the key concepts for this design pattern are that we can add, in effect, any number of behaviors dynamically to an object at runtime by using aggregation as a substitute for pure inheritance. Polymorphism is achieved by implementing a single interface. Aggregation lets us create a stack of objects. Each decorator object in the stack is aggregated in a one-to-one relationship with the object below it in the stack. And by combining aggregation and polymorphism, we can recursively invoke the same behavior down the stack and have the behavior execute upwards from the concrete component object. Not only does the decorator design pattern let you dynamically modify objects, but it also reduces the variety of classes you would need to write. A larger codebase not only takes more time to complete, but is also difficult to maintain and can reduce the flexibility of your system. You want to have a robust system, but without the headache of having an enormous amount of code to write and look after. Using design patterns like the decorator pattern will help you create complex software without the complex overhead.